Please be online. Our next expert will be join us shortly.
Dear participants, good evening. Our next expert will join us within a few moments. Kindly bear with us. Thank you. Dear participants, I had a word with the expert, Dr. C.P.PAUL. He will join us shortly. He's in the process to connect. There is some connectivity issue. Within 4 or 5 minutes, he will join us.
Narendraji,
Sorry for inconvenience.
Narendraji, good evening. This is Dr. Paul speaking. We already joined this meeting.
Thank you, Paul, sir. Thank you.
Good evening, sir.
Good evening.
Good evening, sir. Good evening.
Good evening, sir. Dr. Paul has already joined us. Dr. C.P.PAUL is a leading research group in area of additive manufacturing technology at Raja Ramanna Center for Advanced Technology, RRCAT. He is recognized as one of the top scientists worldwide successfully for the last 5 years, 2018 to 2023, in the list prepared by the Stanford University, US, and published by Elsevier. Dr. Paul has 25-year year of experience in the research and development of laser additive manufacturing, from system development to its applications in engineering. His research program focus on next generation additive manufacturing system and processes. He is instrumental in promoting laser additive manufacturing technology in India through collaboration with other national labs and reputed academic institutes by extending the original development facility for experiment. He has published 26 book chapters. He has published more than 150 such papers in peer-reviewed international journals and presented his work in more than 250 international and national conferences. He authored a textbook on additive manufacturing for undergraduate and postgraduate students. Dr. Paul is founding director of AIC Alpha Hub, Pi Hub, Incubation Center of Raja Ramanna Center for Advanced Technology. He earned PhD degree in mechanical engineering on laser additive manufacturing of engineering components in 2005 and was a research professor at the University of Waterloo, Canada during 2006 to 2008. His efforts have been recognized with many awards, including the highest DAE Excellence in Science, Technology and Engineering Award, Homi Baba Science and Technology Award. Over to you, sir. Thank you for joining us.
Thank you, Gurveer Singh, sir, for the nice introduction. And I'm really happy to be with you to discuss about what are we doing, how the things are being done. First of all, I'm sorry, a sincere apology, because yesterday I wanted to make the things to the next level, but because of some other appointment, I was stuck and could not be done. But today, yes, we will be talking here. So let me share the screen so that we can start talking on the subject of the day. Are you able to see my screen?
Yes, sir.
Okay, great. So again, as you all know that this is the 6-day faculty development program on additive trends in additive manufacturing of advanced materials for industrial application, and being organized by Amritsar group of colleges. Thank you very much for inviting me on this day to talk about what is happening and what are we doing and how the things can be done. So today the title of the talk is Design for Additive Manufacturing. But what I'll do is I'll just go to the more on the basics and try to give it the full insight how additive is making the difference, which is not talked earlier and maybe in a different flavor. So before I start, let me start the talk with a special tribute to our founder, Dr. Homi Jahangir Bhabha. He had very clearly mentioned that if an Indian industry has to take off, be capable of independent flight, it must be powered by science and technology based in the country. And we are trying to work and do the justice to his words, making India a self-reliant. And definitely, we all are want to make the dream realized by 1947 when India became a developed nation. So we have a humble team, pretty balanced. We have around 17 people as an employee, and then we have 6 PhD students working on us with us on different topics. And really, it's a very vibrant group. Everybody's contributing in a big way. So what my presentation overview today is all about, just a brief introduction what DAE and what is the RRCAT, because many of you may be aware, but it's good to just quickly revise and talk about so that we all know how the things are going to be planned and shaped and make the things different for the world. So I'll just share you the lesser known facts about Department of Atomic Energy and at RRCAT. See, this is a slide which tells about what DAE, Department of Atomic Energy, is doing. See, we all know that it is known for power generation and national security. But here, things are much beyond. And if you see in this slide on the left-hand side, we have power. So you see in nuclear power, we are starting from mining to exploration, uranium mining, milling, then nuclear instruments, equipment development, nuclear power plant constructions, operations, reprocessing of the spent fuel, and waste management. So a whole cycle is taken care by Department of Atomic Energy. But this is the main, is considered to be made portfolio. But DAE is also doing a lot of things in the fundamental research, mega science collaborations, research reactors, particle accelerators, radiopharmacy, cancer treatment, and advanced crops, food preservations, clean water, urban water management, and industrial isotopes. So all these things are the part of Department of Atomic Energy. And if you see how it looks like, it has got R&D centers, it got public sector, it has got industrial organization, it has got service organization, and many aided institutes. So beauty is, whenever we talk of the cancer in India, probably we always be thinking of Tata Memorial Center, Mumbai, for the one of the destination where we can go and get it resolved, right? But very few of us know that this is also the part of the Department of Atomic Energy, who is funding in a big way to make it happen. Now we have so many other institutes coming in. For example, we have Homi Bhabha Cancer Institute at Varanasi. Then in Punjab also, where we have come. So what I'm trying to do is that things are spreading, and with the help of the Department of Atomic Energy and the technology which is developed ingeniously. In all, we are 34 units, 6 research centers, 3 industrial organizations, 5 public sectors. When I talk of the public sectors, you see we have Nuclear Corporation of India, Indian Rare Earth Element, Uranium Corporation of India, Electronics Corporation of India, which is known for making our electronic voting machine, then Bharatiya Navikiya Vidyut Nigam Limited Kalpakam. So much things are being done, and we have now 4 incubation centers in the and DAE, and 11 granting institutes and 2 boards. So let me tell about a bit about the nuclear power generation. Whatever we studied in our 12th standard, we know that we take a high Z atomic number nuclei, and we break into 2 smaller, and then we get the energy. That is the way power generation is done by nuclear fission, and that is very common into this. And India has got 3-stage program. I am not going to talk about, but what I want to highlight only here is we have now reached to the stage 2. The moment we achieve the stage 3, the India will be self-reliant, and we need not to go to anybody for the fuel. See, in India we have around 32% of global resources of the thorium, and we have only 2% of the nuclear, 2% of the uranium with us, and we constitute 16 to 70% of the global population. So it's wise for us to run our reactors on the thorium. So a lot of things are being done and running these things. We already reached to stage 2, and the moment we enter into the stage 3, we will not be going to anybody for any nuclear fuel. So that's going to be very great, and that is where India will be likely to go there. If you compare the 3 things, like you take hydel, nuclear power, and the coal-fired, you see when we talk of the hydel, we have submergence of 2,000 to 5,000 hectares for 1 gigawatt hydel power. Similarly, if you talk of 1 gigawatt nuclear, then only 20 acre land is required. And if you talk of the fuel, then we are only using around 12 trucks per year, and emission is negligible because a lot of things are done, and wastage is almost less than 1 ton per year. So now we are taking 120 ton of the fuel, and wastage is coming as a 1 ton per year if you go the nuclear. Similarly, if we talk about the coal-fired energy, then you see for the same 1 gigawatt, you need to have 70 hectares. Then you need around 2,000 ton coal per day, so that things goes, and a lot of emissions are there, and a lot of air generation is there, which is again a 1.2 million. So nuclear is a green way where the future is, and a lot of things are being done in this direction. But what we are doing is, I'm not talking to you a lot about the nuclear, but we'll be talking about the radiation and isotope that we work on. We take these radiation isotopes and use for many applications for the human life. For example, biomedical industry, hydrology, food and agriculture research. So much things we are doing, and this is also being done for the crop improvement, the food preservation. In the crop movement, what we do is we radiate the seeds with the radiation and see how the mutants are coming out, and after that these mutated seeds are harvested, and then we see how the things are coming, and if there is improvement, then these seeds can be taken for the next generation, and 6th generation we tried. That is the way it works, and this has really given a big advantage in terms of the higher yield, drought resistance, high salt tolerance, early maturity, disease resistance, dwarf and variety. A lot of things are being done this, and what our vision for the Amrit Kaal is, but we should have 120 plus varieties of the seeds from radiation in the country by 2047. Today we are having 55 plus varieties, 55 varieties which are already in the market. And whenever you talk of the eating dosa and idli, you must be knowing, the urad dal that is used in this particular making this stuff, and all are coming from the seeds which are irradiated and mutated at using our technology. And because if you compare the normal urad and desi urad and then mutated urad, the yield is 5 times higher. So all India across the country, these things are in, and this is again a very good thing. We are also using radiation processing for many other applications. For example, phytosanitary treatments, where in the radiation mangoes to export it to the United States and the Europe. See, some 12 years back, the export of the mango was around 270 tons from India. Now it has crossed 3,000 tons per year. So this is see that this big change has come because of the radiation technology that we are using. We are using for the hygienization of spices in the flesh foods. Then we are also talking of shelf life extension of the chicken, meat, and the fresh by radiation, insectification of the cereals, pulses, and dry fruit. And these are also being used for the sprout inhibition for the onion, potatoes, ginger, and garlic. So many things are being done by the technology, and this is a really big challenge, and which is not known to the public domain, that DAE is doing all these things using the radiation technology. We are using this also for the radiopharmaceutical applications, and these things are being used in many applications. Many nuclear medicines are in the market, which are coming to the India with almost 10 to 50 times less than the cost of the imported medicines. BRIT is the Board of Research in Isotope Technology, is making this and supplying across the country by many things. And it's a really thing. Some of the isotopes having life of the 3 days, and what is happening, the things are transferred in such a way within 2.5 days or 2 days, it reaches to the hospital so that it can be administered to the patients who are deserving. So all these things are the part of this, and healthcare being a lot of things are done. We are also working on the water desalination and the purification. 2 plants are already commissioned. One is in Odisha, another is in nuclear desalination demonstration plant at Madras Atomic Power Station. So these are the things which are being done and making the things different. We also have the technology of sludge hygienization and Nisurgana. In sludge hygienization, we have already put one in Vadodara. Another plant is also put in the Indore. This is for the cleaning the, whatever the domestic waste we get it, and then we clean and get the fresh water. This is we are doing. The same thing is with the Nisurgana. Whatever we are getting from the kitchen waste, we are using for the making biogas generations. A lot of things are being done, and many plants are built this. RRCAT is known for service to the mankind. We are having majorly non-nuclear frontline research area programs, especially lasers, particle accelerator related technology, and pretty good balance. We have around 1,500 plus employees. We have around 120 PhD students, including departmental candidates, and we have 140. We provide MTech projects assistant to more than 140 students every year, which are coming from different engineering colleges and institutes for the final year project in the MTech and MSc program. When you talk of the particle accelerators, we have 450 MeV and 2.5 GeV synchrotron radiation source. We are using these electron radiation sources for various applications. We have also developed electron LINAC, which are being used for many applications, including the sterilization of medical devices. The import of the medical devices has been reduced because of these plants and working on this. In the lasers, we are everywhere. Wherever we talk of the lasers, RRCAT has got a special role, and all these things are bringing a big change in the technology associated with the RF and microwave, cryogenics, optics, instrumentation and control, ultra-high vacuum material characterizations. So this is all we are talking of. And when you talk of the particle accelerator, probably you will be thinking what the particle accelerator is about. This is a really very complex technology that we have developed here in India at Indore. This technology is like what we do is we take the electron from the atom and we make them rotate in some defined way. For example, from microtron, here we take the electron out, then they are taken to the booster and they are running here at the speed of the nearly equal to the velocity of the light. And in Indus 1, the energy of these electrons are about 450 MeV, 125 milliampere is the current. And here also in Indus 2, and all these radiation, whatever is emitted, because what happens whenever these electron gives a change in the momentum, by changing the direction, velocity is not changed, then radiation comes out, and these radiations are used for various applications. So we have so many beamline in the Indus 2, and though we are contributing in a very big way for the testing of all the satellites which are going, because all these satellites are exposed to very bad weather condition, especially if we talk of the project our mission Aditya, in which we are going to the solar. Many parts are tested at Indus 2 beamlines, and these things are being sent, and these are at Indore. You see typical how the hatches in the beamline looks like, a bird eye view of this. This is the figure of the E-beam radiation facility that we have at Indore, and we are using a lot of things into this and in the public domain and providing this. Now we are transferring this technology to industries so the thing can go and taken to the next level of the program. Similarly, we have lasers. We all know that laser means light amplification by stimulated emission of radiation. So what happens is, like, you have we know that there is an atom. In atom, we have an electron which is revolving around the nucleus, and when the energy is given, it goes to the higher orbit and rotates or revolves around here like this. So this is the lower energy state. This is the excited state energy. This is again a 12th standard stuff. But thing is, when this guy is very unstable here, he doesn't want to be there for a longer time. It emits the electron. It emits the photon, and electron jumps back to the lower orbit, and there is a radiation. This is called spontaneous emission. But consider the case when you have an atom which is already in excited state like this, and it is here, and another atom is coming, and another photon is coming, inducing this particular atom to is to emit the photon. So we have two photons now. One is coming from here, another is here. So this process is called stimulated emission, which is defined here. And this stimulated emission, the beauty of this process is that we have two alike photons, and these photons becomes really things which makes it different. So what happens? These two photons goes to the two excited atoms, and we have four photons. These four atoms go to the four excited atoms, and we have a 8 photons. Like that, we keep on increasing the number of photons, and finally a beam is formed, which is really very powerful and has got a property like current, monochromicity, low divergence, tightly focusability, high brightness, high power, high intensity, ultra short pulses. So this is making a big difference, and the difference is such a that many times, when we think of this technology, we always think that if it is make of the photon only, light is also photon and laser is also photon, then what is the difference? I'll say very explicit difference is what is the difference between mob and army. In mob is also made up of human, and army is also made up of human. And the difference is the discipline they have. Like the discipline light is the laser, and there is because of the discipline they have obedience, uniformity, which results in terms of the light, in terms of currents, divergence, and brightness, which make it different and very distinct into this. So we have developed many lasers at RRCAT. A lot of technologies are being done, and we are using this for many applications, including laser cutting, marking, welding applications, especially remotely for the reactor programs. And these things are right. We are also working on additive manufacturing, 3D printing. We have developed these machines indigenously. Now these are being used regularly for various applications. So all these things, and we are working on many mega science projects from from time. If we talk of the time, then from the micros to macro, and you see all the international collaboration program wherever India is participating. The RRCAT is making a big role into this, especially into LIGO projects. We have a lot of things into the fair. A lot of things are being done from where we know about what is happening into the mega science area. So this is the CERN collaboration that we have. We have supplied so many components to the CERN and the Large Hadron Collider at the CERN facility. And as a result, India became the associate member state of Large Hadron Collider Center, which is at Switzerland. So this is making a big thing. You must be knowing this particular machine is related with the term called God particle, and India has contributed very big into this research, and that is commendable. And RRCAT was a nodal agency for making all these things for the supply of this. We have a lot of career opportunities for the DAE. You can join as a scientific officers. You can join as a PhD program. We have very effectively, very nice program for the people with the diploma engineers. They can join as a scientific assistants. Even for the technicians, which the ITI pass people can join as a technician. So a lot of things and opportunities are there. This particular slide talk about all these things. We have a university called HBNI. This university is 6th in ranking in terms of the teaching and learning experience, and 16th in overall ranking. And this university is doing great, and it has got really and we are doing a lot of program in the biology in terms of biological physics, radiation, medicine, medical isotope techniques. So university is doing really big, doing good things and being done in this particular case. So we are doing a lot of things. We have now recently started one incubation center. So we are trying to push everything into this. So let me come back to the topic, which is the additive manufacturing, which we are talking now. And this is the book that we have published. It is with the McGraw-Hill, available at the Amazon and Flipkart in India, and abroad also it's available from Bookswagon and My Books Factory. So this is the books, and the cost is pretty less. It is also recommended by AICTE for additive manufacturing course. And the course is, we try to push whatever we learned over last 20 years into this book, so that everything given in and people can use it. Now, my question is, we all know that how objects are made conventionally. The objects are made either by deformation. We deform it by heating it. We go for casting, or we go for the joining of this, or subtractive operations. So these things are done, and mostly these process after getting the block, we subtractive process dominate the whole scenario and make the things happen in differently. Now, a question comes: why additive has come and how the things have evolved? See, in 1987, the people thought We are doing a lot of in terms of subtraction. Why don't we think of additive? In spite of reducing, we just think of joining. This brought a big paradigm shift from conventional CNC machine to a sophisticated additive manufacturing machine. This also brought a lot of positive thing to mechanical engineering and manufacturing engineering, because the job which was considered to be the blue collar job here in the shed has now moved to the AC rooms as a white collar job and with less number of the people involved. So this is the biggest thing apart from the technology stuff that is being into this. Now, question is, what is additive manufacturing? By definition, ASTM 52900 or ISO 52900, it is a process of the joining material to make the parts directly from 3D model, usually layer by layer, as opposed to subtractive manufacturing, formatting, manufacturing methodology. So it has got 5 criteria for the qualification. First is process of joining of the material. Second is start from the 3D model. It is a usually layer by layer built-up approach. It cannot be classified in subtractive manufacturing methodology and no formative manufacturing methodology. So whatever the process we are talking of, if you want to classify a process and check whether process is additive manufacturing or not, what you can do is you can just write the name of the process, and on the other side you just qualify whether it is happening or not. So 5 criteria are there. First is process of joining of the material. Second is starting from the 3D model data. Third is so if it satisfied all the 5, like you have all Y, then it is additive manufacturing. For example, let me take the first one. Here I'm not talking of the 3D welding. I'm talking of the conventional welding process. If you compare with that, again, it's a process joining of the process. It is a process of joining of the material. Yes. Does it start from the 3D model? The conventional welding process doesn't start from the 3D model, right? It is not a layer built-up approach. Only we are filling this, and it cannot be classified subtractive and formative. This is also right. So out of 5 criteria, we are having only 2 done, other 3 not. Only 3 done, not 2. So we have to qualify all the 5 criteria. You can just put the case, and then these can be a very good example. If you buy the concept, additive manufacturing is a natural way of growth. It's not a new for the world. You see that how a seed converts into a tree or plant. So what are we doing? You have a seed, it takes that stuff all around and grow. Similarly, how an infant become an adult, you see the infant is there, he eats, drink, that do the additive and become the adult. So this is the way. And what I want to say is, additive is a natural way of growth. But since we were not capable enough to handle such stuff, we had been using subtractive as an option. Now, one of the beauty of concepts you can understand, whenever we are making a house and we have a brick, we have mortar, we make them join together like this, and this freedom itself brings such lot of flexibility and shapes in the manufacturing. So you can appreciate how additive manufacturing can make the thing different, and that is the stuff that we are talking and making about here. This is a quick comparison of additive manufacturing, substrate informative. The advantage we have in terms of the lead time, in terms of the material, we have no limitation. In terms of the complexities, logistic freedoms, and we are scoring low in terms of the speeds. We are scoring low in terms of we talk of mass production and making this happen. So where we are, so additive we have to really find out whenever we want to apply. We have to see what is the application and how things can be brought to different domain, and preferably if the technology is very useful when you want to go for a low volume manufacturing. So that makes the life very different. See what is happening. You see how the cost changes when the number of parts increases. If you talk subtractive and formative, the prices are going exponentially down. But if we talk additive, it remains constant and just goes a slow bit by that. So additive manufacturing is a really very good one for having low volume production. And today when we are talking, it's of customized product, it is making a big difference into this. Now question is, why we are talking so much about additive today and how things can be made different. See, this is a different prospect that I am going to share, different perception. Today we have cutthroat competition. I have shown you here the picture of the car on the left top corner, just to represent how the car market has changed in last 35 years. Some 35 years back, we had only two car manufacturers in the country, Fiat and Ambassador. And they were knowing they have assured business and they were not making a lot of changes into the model. As a result, things were not growing so fast. With the globalization, the market is open. Now we have everybody in India, Hyundai, we have Toyota, we have BMW, we have so many Hyundai, then we have many manufacturers, including Maruti and all. And another thing that I would like to highlight into this business is every car manufacturer is bringing so many models. They have compact, SUV, they have SUV, they have sedan, they have compact sedan, they have hatchbacks. So many models. Why I'm talking about this, though the market of the car has gone up, but if you see, because of the presence of the more players and availability of the more models, the net sale volume of the cars per product is reduced. That is the thing which I want to highlight because on this part. And this is making a big difference into the commercial part. Second point is, the people are going for the adverse duty. Let me talk about cars only. If you talk about the cars now, we had BS4, then we have BS6 now. So what these standards are doing, they are making the things more and more complex, trying to improve the efficiency of the machine, giving better results. And whenever we're talking of having a better machine, more challenging machine, it means we are putting a lot of things on manufacturing, other materials to have different, and definitely this is the expectation of the industry. Another big thing that we are seeing in this world is, today we are having a very fast changing technology. See, somebody sitting at some corner of the world, think differently and apply to it, and it collapses whole ecosystem. This is the thing that is happening. One of the recent example is, for example, you talk of Zomato or Uber or Ola. Uber and Ola, how did they change everything into the car market? See, taxi and rickshaw, everything is changed now. Similarly, if you talk of restaurant business, Zomato and Swiggy has really changed. So what I want to say is the small concept. Similarly, have something similar happening into the industries also. People are coming with some novel ideas and they are killing, all jeopardizing whole ecosystem, whatever the balance is. And this is really big thing. And if you talk about the customers, what the expectations they have today is, they want more and more we have more and more variants in the product. That is the thing which is happening. Product that can be sold as it is into the market, the time is reducing. Product complexities has gone up, and immediately delivery of the product is the requirement. Now, to come out of this, the requirement is to have immediate delivery of the best quality product with maximum features at the lowest price. Now, I'm talking about the giving immediate delivery of the best quality product with maximum possible features at the lowest price. All these things are, contradictory. You're giving best quality, you're doing immediate delivery, you're giving maximum, and the price is also low. So, how to get rid of these issues? How to resolve these issues? The very simple to do it is going with the additive manufacturing. How is it going to make the difference? For example, this is a cycle that I am describing on the conventional manufacturing. We have a conventional manufacturing in the design phase. We are going with the synthesis. We are going to analysis. We are going for the documentation and drawing. Then we are going for the production. In the production, we have a planning, procurement of the material, tool procurement, CNC program in manufacturing. Then we are going for the quality control, packing, and uses. So this is a typical cycle that we are following in the conventional manufacturing. The moment you take off the additive manufacturing, we have these 5 steps changed and made the thing very differently. For example, if I talk about the first one, when we're talking of the documentation drawing, since I'm using a 3D model, I am not bothered about the making any documentation drawing. The product which is made is used as it is. So this is the first thing that is making the difference. Second thing is it's saving the time also, right? Then I'm not doing any planning. For example, in conventional process, I'll be thinking what to do, how to make the job, whether it has to go to the machine shop, it has to go for fabrication or some welding or heat treatment, so many steps. But in additive manufacturing, all these machine plannings are done by this, and things are different. Similarly, in the raw material procurement, we are procuring the material in the bulk here. It's the shapeless like wire and powder, which is non in case of conventional manufacturing. So we are buying this material and then keeping in the stock. So that time is saved. In conventional manufacturing, you cannot start the manufacturing unless the design is frozen. But in additive manufacturing, you can just buy the material, keep in the stock as soon as the design shall start printing. So all these things are possible and making it different. And definitely there is no need to have a special tools for manufacturing. It's also making the thing very different. So by saving all these, cutting all these steps, lot of time is saved in additive manufacturing, and time is money. So this way, it is making a big difference. If we summarize the advantage of additive manufacturing, the first one is complexity for free. Complexity for free means you have a complex material. Any complexity you can achieve. See, in conventional manufacturing, as the complexity increases, the cost goes up high and high. But in conventional, the conventional one doesn't change. So that is happening. Second advantage is simplification of part fixturing. In conventional manufacturing, what happens is we are using cutting forces, forming forces, or forging forces, which makes the fixturing very complex. But in additive manufacturing, what are we doing? We are using a non-contact method to fabricate and make this happen. Therefore, our simplified part fixturing becomes very simple. The third is the mass customization, because we are using the process. Every component is one by one. We can design it and electronically, and a lot of customization done, which is not possible conventionally. Fourth advantage is having a integrated component. You can have now some sensors. Since you are making everything layer by layer, sensors can be integrated while making the product. So this makes the life into different domain. The fifth one is material design freedom. You can decide how the component has to build a strong unit strength. Then you can use stainless steel. If you want better conductivity, you can use copper at the place. So all these things possible in a one material itself. You can, in a one component itself, you can have multi-material design, which is a very good feature that has been brought by additive manufacturing. The sixth advantage is having a logistic freedom. Means you can change your model anywhere across the world, take the feedback, it can bump, and also you can decide whether this component has to be printed in India or abroad, or even within India, either this component has to be printed in Delhi or Coimbatore, depending on the site location available to the machine. These can be decided and done it. So this is another advantage in terms of the logistic freedom. Seventh is reduce wastage. In additive manufacturing, you can place the components so nicely nested, and conventionally it's not possible. Therefore, this is also making the advantage in terms of big difference. When I'm talking about the advantage of technology, I should also be talking about the limitation of the technology. So the presently one of the limitation is the production cost is very high. Again, I'm confident with the time things are changing, and as it is going more and more into the large volume manufacturing, the high production cost will definitely going to go down. Mechanical properties is a concern because new materials are being tried, new technologies are, new manufacturing methods are being considered. So a lot of uncertainties in terms of the compression, tension, shear, torsion, and bending. But again, if you take the property of the cast material and go with that, probably your design wise you're safe, but you are safe. But again, it's at some limitation in terms of this. The third one is most of the times you require some post-processing because we are not able to get that surface finish that we are really looking for in metal additive manufacturing. So that is the requirement, and things are done. The fourth limitation is having a limited build volume. Presently machines are like 300 by 300 by 300, or maybe 1 meter by 1 meter. 1 meter, not like the conventional one where you have a very large size machine. But again, these things are being researched, and slowly this limitation will also be taken out. The fifth limitation is the stair stepping effect, because again, it's a layer by layer fabrication. If you take the higher layer thickness, there would be steps like this. If you take the thinner one, there would be less steps. But if you see the features here, the fabric features are bad, but the fabrication time is less. But here, features are fine, but fabrication time is fine. So we have to really make a best compromise between these two to resolve the problem of stair stepping up. So there are 7 processes as per the ASTM classification: wet polymerization, photopolymerization, powder bed fusion, material extrusion, material jetter, binder jetting, direct energy deposition, sheet commission. And there are many. These are the players who are supplying these machines. Now, these are the international brands that I have written here. And all these things are also now being built in India, and slowly things are changing here. So what is the situation of additive manufacturing at the global and national level? So every country is trying to jump into and making the metal additive manufacturing great. And every country has got some or other program. In India, we are putting a lot of things in terms of Make in India. Here you see Make in India. We are doing it. China is having, Australia is having. All are trying to come and work on these under different research program, and therefore that's very great. And whatever ATAL-FDP we are attending, it's also part of the initiative that India is having to popularize the additive manufacturing technology, and this is right. If we talk about the status of the technology across the globe, for the aviation and automobile, we are almost crossing 5 and reaching almost to 6. In terms of tooling, space, and drone, we are at the TRL level 8. And in dental, medical, instrumentation, implant, and artistic area, things are at the full production rate. So full rate production, this is available. So this is the technology. Technology really very attractive and maturing very fast to achieve a new and high. In India, we have already having a national strategy for additive manufacturing, which is released by 24 February 2022. And it has got very specific target that we should have 5% global share contributing $1 billion to GDP, 100 new startups, 10 AM sectors, 3 lakh new skilled manpower, 50 AM technology on material, machine process, and softwares. So this was a target. And if we talk of ourselves, this target looked the very hyped one in 2022. But in 2025, as the things started working on, things have changed and made a big difference because of the initiative that everybody in the country did, including you and me. And if we talk of the contribution of startup from our side, our incubation center has given 4 startups in the domain of additive manufacturing. The target was 100 for across the country. 4 has come from us. We also given a lot of FDP programs. You must be knowing we want to have 1 lakh skilled manpower. So all these things are being done and working on this stuff. We have already put our 3 machines technology transferred. So target was to 50 for the country, and 3 has already come from our lab. So this is the way how technology is changing and what our target from the India have. India is also adopting these technology in a very big way. We talk of the automotive industries. We have giants like BMW, Ford, Tata Motors, Maruti Suzuki. They are working in a big way, and you see the type of things they are using, and we can't think of how things are being done. Same is in the aerospace and defense. Technologies there we have Airbus, Boeing, and Lockheed Martin. They are also doing a lot of refurbishing work in India in terms of the healthcare, construction, electronics, art and jewelry. Now even the food and beverage is making the difference. So many things are being cooked using additive manufacturing technology, and Nestle, Unilever, and Britannia are the lead. In textile and apparel, also things are coming. For example, Nike, Adidas, Puma, H&M. So they are all making a lot of things using additive manufacturing technology. so that thing can be brought to. So additive manufacturing is not only in manufacturing, but it's complete covering complete domain from automotive, aerospace, healthcare, construction, electronics, art and jewelry, food and beverage, textile and apparel. So this is the situation we have today in India. We talk of the metal additive manufacturing across the country. Mostly private industries are focusing on plastic-based AM systems, and academic institutions have very good effort in R&D in laser-based manufacturing systems. RRCAT, CMTI, IRCI, DMRR, GATRE, IIT Kharagpur, Bombay, Kanpur, Palakkad. They are the people like another national like CISRI, CGCRI, Kolkata, IGTR, Indore, CTCT. All these the people have additive manufacturing machines now available for the metals. Many private companies like Wipro 3D, Honeywell 3D, Incredible, Dentacare, GE, Objective, LNT, and many more. They all are working for having machine, and some other way they are contributing to the national building. It's not only making the machine, but there are now many companies or national labs are making these machines indigenously. For example, RRCAT, CMTI, Bangalore, CMERI Durgapur, IIT Bombay, IIT Kharagpur, IIT Hyderabad, IIT Jodhpur is now, PSG Coimbatore, Intech, MS. So all are making a big difference in laser-based additive manufacturing. And people are trying to build thing into this. What most important message that I want to give here, making machine is definitely challenging, but it's more challenging to prove the application employment. And that is the where we need to work, and we all are trying to make the things different in a big way. So this is the way how whole scenario is being changed in the country, and things are becoming different. So this was the very introductory lecture that I have about how additive manufacturing is making a big difference in the country, so that thing can be taken to the next level. So I'll stop here, and I will try to listen to you guys, have some questions if you have, and definitely in the next sessions we'll be talking a lot of many things, how we have worked on. And I'll stop my presentations with a word from Dr. Vikram Sarabhai, where he said, we are convinced that if we are to play in a meaningful role nationally in the community of nation, we must be second to none in the application of advanced technology to the real problems of man and society. And that is where we are trying to do. With this talk, thank you very much for patient listening. If you have questions, I'll be happy to answer you all.
Good evening, sir. I am Dr. Anas Ahmad Siddiqui. I have actually worked with you in your lab. We
Yeah.
have some collaborative research paper as well. I am
Yes.
currently working as an assistant professor in National Institute of Advanced Manufacturing Technology, Ranchi.
Okay.
Sir, we want to establish a lab for this laser-based manufacturing. So, what if you can suggest us some good different companies that are based in India through which these things can be purchased? That would be helpful, and I can at a later stage, maybe I'll message you or may get in contact with you so that we can work on that.
Anas, thank you very much for the very good question. See, we have now 3 startups working with us in metal additive manufacturing, and 2 more are to join. So we are working on this, and like we have people like we fuse metal for manufacturing is again startup, and then we have Unnati 5D Unnati is a Mumbai-based startup working with us. We have Mira 3D, another software development companies, and so we have these companies, and they are giving the stuff in very promising price. What will I say is maybe you can write to me, or we can have one-to-one conversation where we can think of how what is your specific requirement, and maybe I'll just try to connect with them and push your case so that you get a very good price, and what are the budgetary allocations you have. Accordingly, we can plan. This can be done. Not a big deal. Thank you very much.
Surely, thank you, sir. Thank you.
Yeah, I could see, Manik, your questions to improve the surface properties of inconels and when comment, which way is better, optimization of ED parameter or biometric structure? See, as far as I'm concerned, first thing we have to think, what is the surface property you are looking for? What is the surface finish, or what are the strength point of view you are looking for? Accordingly, we have to go for the solution. So if you talk about the properties, for example, you want to have a very good surface finish, then definitely some post-processing operations has to be carried out, like maybe the machining, or maybe we have now slurry surface preparation methods. Many methods are there. So we can use these methods to improve the surface property. That is one part. Second, if you want to really work on the so there is another thing which we are making the lab different is how if you are talking of not the surface property but the bulk property, then definitely optimization of parameters is going to make a big difference. And especially directed energy deposition machines, now how you have scan speed and the rastering patterns, these are going to make a big difference. So if we can work on these 2-3 things, definitely think can be taken care and better results we can have. So optimization of process parameter is really good if you want to go for a improvement in the bulk property. But if you are just focusing on the surface properties like surface roughness or maybe hardness, then maybe we can go for some post-processing applications.
Okay, sir. Thank you, sir. Thank you very much, sir.
Thank you. Any other question?
Sir, one more question, sir.
Yeah, please.
Yeah, while using this direct energy deposition for the deposition, so there is a residual stress generation.
Yeah.
So to reduce this residual stress, what are the different techniques we can go for?
See, for us, what is the layer-to-layer rastering pattern you are changing now? What is the
Actually,
scan pattern?
actually, we are using unidirectional only.
So that is the first thing that is the problem. So what can you do is you can have a rotation of the all rastering pattern by 67 degree on every layer.
Okay, okay.
So what will happen? First thing which will happen is, see, once you are making a unidirectional deposition, there is a accumulation of stress in, say, for example, your movement is on the x-axis. So your everything will be accumulated in the x-axis direction. But if you rotate it by 67 degree, then you are just changing the direction of the stress in every layer. So this helps in resolving the issues in very big way. And this is very much proven fact. So that can be done, and that will make your life simple. But again, once you are making a block, probably it is easy for you to do it. But when you talk about making some complex components, for example, you are making some rotor, and in that again you have to think whether strategy for the 67 will do or not. But beauty and bigger advantage we have is whenever because the strength in the linear direction is always better. Like in the x plane, it will be higher as compared to y and z, and definitely we can take the advantage of this. And again, the difference is not very large in most of the times, especially in kernel 718. It's around 15 to 20%. So again, we can accommodate also in the design criteria. But if you want to really take the advantage of the design, then it's good to delay the track in the direction of the stress that you are looking for. That is the way it is done.
Okay, thank you very much, sir.
Thank you.
So I will write an mail if I have any doubt regarding this.
Please, you are welcome to answer. What will I do is I will connect with some of our team members, because
Okay,
many times happens there is a delay if I have to reply. So
No
what
problem.
I do is I forward it to my team members, and the questions are straightway you can get. And if there is anything which has involved some more complex, then definitely I reply. But you will get the reply. Please do write to me.
Yes, sir. Thank you very much, sir.
Thank you.
Sir, what are the common defects observed in additive manufacturing, and how can they minimize?
Yeah. See, there are many common defects. For example, let me today, yeah. I was thinking to talking about it in the next talk, but again, we'll speak today. See, the talks, the problem that we see is there is something like inter-run porosity. If you do not have, if you don't have, nice overlap index, which has to be optimized between 55 and 47, or you don't have aspect ratio of the track, which has to be more than 5. Aspect ratio of the track means once you make a line, what is the height and width of the track that you have deposited? The width has to be 5 times more than the height. That is the one of the things. If you don't meet this, then there would be something like inter-run porosity. Sometimes what happens, the powder itself having some pores into it, and when you melt and deposit on this, then gas porosity is generated. That is another problem that we are seeing. Third problem that we see is the delamination of the layers. Once you're depositing, like Manik asked the question, how to reduce the stress. Now, if the stress generated within the material is more than the ultimate strength of the material, then it's likely to delaminate from there. This is the third problem that we see. Fourth issue that we see is the problem of the oxidation and some foreign intrusions if things are not done in very systematic and a big right way. For example, if you are working nickel alloys are fine, like in furnace solvent, there is no issue. But if you use material like titanium, or you use some other material I should say niobium or zircon, which are like needs a really very good control atmosphere to work on it. For example, magnesium alloys. So the chamber has to be made in a very nice way. You have to achieve the purity so that these things are, and these are the way how it is removed. But any negligence, any state of time is the problem. These are the three. And fourth is if you do not plan appropriately, there will be distortion. Specifically, if you want to make a circular hole, it may be elliptical, and all these things we need to take care during the design of that stuff, which need to be answered. So these are some of the common defects we do it. And as far as the porosity is concerned, many times people send it for hipping, so that what isotopic isostatic pressing, hipping people go for it, so that this is reduced in some big way. So there are ways to do it, but again, these are common defects. If we don't care during the fabrication itself, then we are going to end up in big problems. So that is really reflected.
Sir, can we use superalloys for the additive manufacturing?
See, like many superalloys people are using. Inconel 718 is one of them. Inconel Stellite 694, and then Hastrolite. We have used Hastrolite. If you see in my publications, like we have already worked with almost 18 superalloys in different level, and all these things are, and all for very exotic applications. For example, if you want to make a Hastrolite, then especially making microchannel heat exchanger, which was not thought of. Then in Inconel 78, we are working for this, and things are good. Especially when you talk of the superalloys, when presently we are working in one project for ISRO. There is a plan from the ISRO to build a rocket engine for a rocket. The name of that rocket will be Surya, which is likely to be launched in 2032. And it needs 26 rocket engines. And India can, as of today, make only 3 rocket engines as per the capability we have. So they have asked us to work on this project using additive manufacturing technology. So we are sharing with them, we are working on it. And specifically, these rocket engines are very challenging because you have bimetallic stuff here, you have a copper and carbonate with typical cooling channels, and many things are there, very strong features. So we are working on this. And size of these engines are pretty large. The 1:1 size, the largest one will be about 2.4 meter diameter and 3.2 meter height. So you have to really make such a large component where thing can be done. So we are working on it. And super alloys and other things, if you don't do it using metal additive, definitely we are on the disadvantage side. So we are doing a lot of things that can be done. Yeah, please.
Yeah. Good evening, Dr. Paul.
Yes,
First of
please.
all, I'm really thankful for the very informative session. So my question is, how do material properties influence the selection of an AM process? There is some process for the additive manufacturing. Is there any properties which can influence that?
In this, I'll say like this. Additive manufacturing brought a new design concept, which is called feature-based and design in manufacturing. Earlier, what was happening, we used to think, what do you want? You want to think, suppose you in a component, you want to have strength as well as corrosion resistance, then you will go for the best available material, which can be corrosion resistance and strength. So you try to compromise on that. And first thing that additive manufacturing did is it changed that whole scheme. Now we are thinking of depositing the best corrosion resistance material into this, and then wherever you strength, you can have the best. So the combination of bimetallic, trimetallic, all these things is possible, which make that thing into different. That is one part. Second thing is, while you are selecting the material, you have to look for a feature that we are looking for, what a property we are thinking. That is the major criteria, number one. Number two, whenever you are using 2 or 3 materials, because you are going to join them, you have to think of how compatibility of these materials. For example, if you talk of moly and then copper chromium zinc alloy, they do not gel well. Similarly, if you talk of stainless steel titanium, they do not gel well. So depositing them and making the component out of these 2 dissimilar materials is again a very challenging. So we have to think of how metallic bonding these 2 materials are having. Again, see, as far as you are working with a single material, the life is simple, because the properties like thermal conductivity or coefficient thermal expansions and all these things are not creating a lot of issues. Even the melting point is not creating the issues. But if we talk of the additive manufacturing, if you have a copper, which is at the melting around 1000 degrees centigrade, and you have another material which is like you have tungsten, which is melting at 31, 32 degree, 100 degrees centigrade. So by the time you reach to that temperature to melt that tungsten, the SS is already, copper is already, into the vapor regime. So these are the properties that you have to see, and you have to come and brought to them to certain level. As far as the temperature difference of say 600 or 500 is concerned, in most of the cases, additive manufacturing, we are able to manage. So the answer is, you have to look for a thermophysical properties and metallurgical compatibility of these two to start up.
Thank you, Dr. Paul. My one question is, in between your presentation, you said that you are also providing the training opportunities to the students.
Yes.
At your atomic center, right?
Yes.
So is this for the BTech students also, sir?
See, what is happening in country, we have a large number of the BTech students coming in, so we are not promoting them a lot, because and moreover, if some BTech student who is doing and plan to work with more than 6 months, for example, many institutions have started now. What they do is they talk of the credits, and suppose the student has to earn 160 credit to earn the degree for them, and the student is able to earn all these credits in, say, by 7 semesters, then 8 semesters is free for the work with us. So if the project duration is, say, 4 months and beyond, even UG students application be considered. But otherwise, if they come here for 30, 40 days or maybe 6 weeks, so the people who are working, they do not get a lot of advantage into this, but definitely we can make them visit to this, and they may not be learning a lot. So for a proper learning and having a involvement in the system, at least 4 months is required, and which is not possible for the EUG students. So that is the thing that we are doing.
Thank you, Dr. Paul. So what is the process to apply for that? As you said that there's a 4 months training option can be provided at your end. So how the students can apply for that?
I'll just share the link. Just let me. If you go to, let me share the link so that all are.
Yes, sir.
Just a minute. Let me open the web page. I put the link on the chat box so that all will be benefited. So this is the link. You can use this. So what you have to do is there is some standard pro forma in which you will have application as well as the endorsement by your college. So student can apply to this, forward to us, and depending on the availability of the seats, this can be.
So is there any certain CGP is required for to apply for this?
I'll not say that way is something that we are really too hard, because sometimes the students with the lower CGPA do much better than the people who are having high CGPA. You know, that is also one of the things.
Yeah, it's
Because
absolutely true.
scoring in the exam is a different ballgame than really knowing about the subject. So what we do is normally once people apply, we connect with them with the potential supervisor, and then the supervisor, and then they have some small interview, and they try to see what is the potential they have, what is the seriousness the student has. Based on that is correct. But for sure, if you talk of one institution, for example, you talk of the Guru Nanak group of institution of the schools, the colleges, then from the same colleges we try to accommodate in the merit wise, so that there is not much issues involved into that part.
Thank you, sir. Thank you.
Ubed has written me, thank you very much for reading my book, and really I'm happy that you learned some of the things, and then hopefully the next session that I'm going to take on 7th will again be making things better. This time things are more on the reduction part, but definitely we'll be going to talk about a lot of things into the design aspect.
Sir, can we done post-processing of additive manufacturing parts? Is possible?
I will include in that session itself, because normally my modules are for the 1 hour or so. So I can extend it to 1 hour 20 minutes, and we can put the post-processing part in that.
Sir, thank you. Any question from audience?
Which course are available at our ARCAT? No, Hitesh, we have a different thing into this. Definitely, we're going to have some online courses in additive manufacturing also. But see, what you have to do is when you see the courses which are available, maybe you go to the site if you're, based on your interest, whatever the RRCAT is working, you can find out, and then we can take this. So courses are mostly on advanced areas like additive, then you have RF technology, ultra-high vacuum, and so people are doing on those areas, not the thing that may fall into the use areas. Another question I'm seeing is about biometric structure of VAM using magnesium. Gautam, this is really very challenging that you are talking of. Magnesium is not straight material to work on. I think you all appreciate this. It's a highly oxidized, and then working in upper atmosphere, especially VAM, is really challenging. Getting shielding and all is all said and done, but we could do in our chamber with us, because we have a controlled atmosphere chamber. In this, these things can be done into this, and definitely oxygen level and moisture level has to be brought less than 20 ppm into this, and it can be done. So I will say that VAM is doing as possible. If you can achieve local at inert atmosphere where the oxygen and moisture level is less than 20 ppm, either you do in chamber or you do in open atmosphere, it doesn't matter. So focus is on how the beauty you achieve. That is something that we have to work on. Gautam, I think I answered your question. Snehshil, this is really good. Environmental impact of additive manufacturing is really 2-3 things that we have to consider on this point. One, can the material be recycled or reprocessed, which is the case, which is really making a big difference. Another thing is how energy is being used, because we are also talking to have less effort. So these things are important. Now, what is happening whenever you're talking of components which are having a better serviceability or repairing or refurbishing opportunity, these components are going to definitely in favor of our environmental impact. So this makes the life do into this. And another thing is how the energy is being used at different levels. Today, I will say that in most of the applications, whatever we are using, we are looking into a lot of recyclability of stuff. So the things are in really well under control. So that is a part of the game. But again, nevertheless, a lot of studies are there. And I think I have written one paper. Yeah, I have written in one paper on Journal of Clean Production Technology, Clean Production. There we are talking of how it impacted the dye manufacturing using this technology. So that paper already will have more data about this. Himanshu is asking one question, asking it the scope of additive manufacturing in C.P.PAUL project, or the opportunity related to the additive. See, I'll tell you how additive manufacturing is making the difference of the additive manufacturing with C.P.PAUL. I'll give you 2 examples. One of them is definitely from ISRO, that is Surya, that in machine we are making. ISRO contacted us, talked to us. We were discussing on those aspects, and the ballpark figure that given to us by us to them is for the building machine is around 10 crore. And they happily agreed because of the 2 reasons. Number one, they can have nominations directly to us. That is number one. And number 2, they got very good price. When I talked to them and asked to the what is the price that they are getting from foreign people, those who are committing making these machines, the cost given to them is 82 crore plus. So you see the difference. We are talking of 12 crore and 82 crore. That is and once we are having multiple entities like this, definitely is going to make the difference of contribute to the. Another example I'll tell you, in one of the defense applications, we were making one gearbox. The startup is working into this. This particular gearbox has got 11 gear into this. And we are buying these from our Eastern Europe friends. And the cost of these gearboxes is around 52 lakhs. And they do not sell us spare gears. They send, they don't sell spare gear, they send all gearbox. The cost of the gearbox is 52 lakhs, and only 4 particular gear they worn out very fast. So we have to buy every time. The armed forces have to buy a full gearbox from them and keep in the stock. That was going on. When we came to know about it, we started working on it. We worked with them and then tried to develop these gears here. And the materials were different. We were not knowing the material. We did the reverse engineering. We tried to identify. Then we got some equivalent material from the Europe and America. Got it tested. Made the gears. Get it tested in our lab. then we given to the armed forces to work on do the testing. The armed forces asked us how much money you will charge. The company said they will be looking for around 1.2 lakhs rupees for each gear. So now you talk of this, a gearbox having 11 gears costing 52 lakhs, and people are not ready to supply the spare gear of the particular number. And we are giving in 1.2 lakhs for the same gear. This we did and made it happen. After 10 days or 2 weeks, our friends in the armed forces got a letter from the India's friend on the Eastern Europe, asking that they are ready to supply these spare gases now in 8 lakh each, considering the long-term association we have with them. Now, this small change by making a gear where we are able to make these gears in 1.25 lakh, and now because we could make it, we are getting a similar gear from the manufacturer now at 8 lakhs. So now we have an option whether to go for a gear of 8 lakhs or 1.2 lakhs. So this is the power that India got just because of a small change that the things happen in the lab. And this is making, and when you are talking of the thousands of the gears which are used by the armed forces, then this numbers becomes really significant, you know. So I'm talking of the contribution by additive manufacturing to these levels where we have a broad blocks in terms of technology and self-reliance where they are going to make the difference. So no doubt additive manufacturing is going to make difference. I think you are also asking another question is what is the scope administration? Bharat, additive manufacturing in terms of funded projects. See, funding projects, again, I'm saying, please understand very carefully, building a machine is one game, making the component is another game, and deploying and proving application is important. See, when I'm giving the example of the gear that we built and our startup is giving it to armed forces in 1.2 lakhs, it's not only making and building the gear, but doing a reverse engineering to identify the material, making this reasonably good, do the all testing, and deploying it and show the demonstrated is because see, armed forces people they say, "Arey, mujhe to chala ke dikhao, I'm not bothered. You know how does it come?" And that is the thing we have now in the country. So we have to really focus on these matters and make the things in such a way that whatever we are doing, we have to prove the effort. And if it happens, one should not bother about the lack of funding in these areas. Government is putting a lot of money into this. A lot of projects are coming into these areas. ISRO is asking this, then IDEAS is asking, ITAX is having some projects into this. So sky is the limit, provided we should be able to prove the application and prove the worthiness of the technology that we are trying to do. I think I answered you, Hitesh. Yeah, thank you.
Yeah, thank you so much, sir. Thank you so much.
Thank you.
Any question? Participants, I think all are covered. Thank you, sir, for this wonderful session. We will be meet in next session.
Thank you. We'll work on it, and as you requested, I'll be talking both the topics, a insight about the design for additive manufacturing as well as post-processing part. So thank you very much. Good night. See you on 7. Thank you very much.
Thank you, sir.
Thanks a lot, sir. Thank you.
Thank you, sir. Thank you.
Dear participants, thank you for your active participation today. We had insights sessions, and I appreciate your dedication and engagement. Tomorrow we will continue with more valuable discussions and expert talks. So I encourage you to join on time. The link for the tomorrow's session will be shared in your WhatsApp group. I once again thanks to Dr. C.P.PAUL ji for this wonderful session.
Thank you very much. Thank you.
Thank you.
Dear participants, one more thing I want to convey. This is Dr. Narendra Sharma, working as a Dean Research and Development in Amritsar Group of Colleges. One thing we have noticed during the attendance time, few of the participants has not joined with the same name and the email they have registered at the ATAL portal. So kindly be sure that otherwise there may be some issue in the attendance. And if the attendance is not made accordingly, there may be certificate will not be issued. So I request all the participants, please join with your name and email what you have registered at the ATAL portal and stay for the whole duration, as minimum attendance required for the qualifying for the certificate is 80%. Thank you. Thank you, dear participants.
Narendra sir, actually, I have registered in this Atal portal using my mail ID provided by the institute. The same mail ID, I am not able to log in through that mail ID, so I am using a Google Gmail ID, which is an alternate mail ID. That mail ID provided by the institute is basically Microsoft mail ID, so I'm
Okay.
not able to log in through that.
This you have joined the ATAL-FDP very first time, or earlier you have also joined from that email ID?
Earlier, I have also used the same mail ID, but they were using the Microsoft platform. So on in the Microsoft platform, it was that mail ID was working, but with this Google platform, it is not working.
Okay, with the Google platform, it is not working.
Yes, sir.
Okay, got it. So anyway, we will note down the issue and we will write it to the AICT officials for that. So any other issue? Otherwise,
No,
this is being noted and we will definitely communicate to the AICT officials.
yes, sir,
Rest,
sure.
my again appeal is the same. Try to register with your name and the email ID what you have registered on the ATAL portal apart from this case. Thank you. So we will meet tomorrow, dear participants. Good night.
Thank you.